In this video, we will do some antiderivative examples. So I want to begin by writing some basic antiderivative rules. And I want to do this in this table. Okay, so one of the columns for this table, the middle one has a function f of x. The one on the left has the derivative f prime of x. And the one on the right, capital F of x, that is an antiderivative of little f of x. Okay, so let's start with a function of the form x to the n. So the derivative of that, using the power rule, is n x to the n minus 1. The antiderivative of this, we could do it with a little bit of guess and check, but the antiderivative of this is going to be x to the, this is what's called the reverse power rule. I add 1 to the exponent, and then I divide by that number. So I divide by n plus 1. And I could check it, if I were to do the derivative of, this is the same thing as 1 over n plus 1, x to the n plus 1. If I were to take that derivative using the power rule, the power would come down, it would cancel with this 1 over n plus 1. I'd subtract 1 from the exponent, and that would give me x to the n. So this is the reverse power rule for antiderivatives. And this works as long as n is not equal to negative 1. If it was negative 1, I'd be dividing by 0, and that would be bad. So what happens if n is negative 1? If n is negative 1, we get x to the negative 1. And that's the same thing as 1 over x. And the derivative of that is just power rule. We bring the negative in front, and then get x to the negative 2 by subtracting 1 from the power. And the antiderivative of 1 over x, we would have seen this before in Math 30, or in the calculus class you took before this. And in that class, you might have seen that it was ln of x. I'm going to be slightly more general. I'm going to write ln of absolute value of x. Okay. And one of the reasons why I'm doing this is that absolute value of x lets us define the derivative of ln for negative values. Once I put the absolute value there, now I'm able to plug in any positive value for x or negative value for x. I just can't plug in 0. And the same thing is true with 1 over x. I can plug in positive or negative values, just not 0. So of course, that doesn't technically explain, why is the derivative of ln of absolute value of x equal to 1 over x? It's just more a way of confirming, they have the same domain, and that sort of is good. But we could prove the derivative of ln of absolute value of x is 1 over x with just some basic piecewise functions. It's not too challenging. So I'm not going to focus on that in the video. Instead, I want to focus more on other basic derivative rules and doing examples. Okay, so let's do e to the x. If I have the function e to the x, the derivative of that is just itself. So the antiderivative is just itself again. And also one thing to notice about this table is when I write f of x here, capital F of x, I'm just writing an antiderivative, one antiderivative. I'm not writing the most general one because I'm not writing the plus c in all of these. Okay, what about if my function f of x is the sum or difference of two functions? What if it's something like g of x, either plus or minus another function h of x? Well, the derivative of that would be just the derivative of the first, and then either plus or minus the derivative of the second. The antiderivative of something like this is just the antiderivative of the first, which I'll call capital G of x, and then either plus or minus the antiderivative of the second, which I'll call capital H of x. Alrighty, what if I have a constant c multiplying my function g of x? Well, the derivative just keeps the constant in front, and then I multiply by the derivative of g, which I'll write as g prime of x. The antiderivative is similar. I keep the constant in front, and then I multiply by the antiderivative of g of x, which is capital G of x. So in this formula, c is a constant. C is a constant. All right. Now what if I have e to the kx. So something slightly more complicated, e to the kx. Well, with e to the kx, the derivative of that requires the chain rule. So the chain rule will give me e to that power, but then I have to multiply it by the derivative of the power, the derivative of the exponent. And the derivative of kx is just k. So the antiderivative of e to the kx is going to be e to the kx, but instead of multiplying by k, I would divide by it. So I'd get 1 over k in front. And I could check this if I wanted to. If I were to take the derivative of 1 over k times e to the kx, using the chain rule, well, I'd still have the e to the kx there, but when I multiply by the derivative of the power is just k, and that k that comes down would cancel this 1 over k in front. All right, so that's good. So in this formula, k is also a constant. K is a constant. And then finally, what if my function f of x either looks like the product of two functions, so g of x times h of x, or the quotient of two functions, so g of x over h of x. So if you multiply two functions, the derivative involves product rule. So I get the first function times the derivative of the second plus the second function times the derivative of the first. And when you divide two functions and you take the derivative, that's quotient rule, you get low d high minus high d low all over low squared, all over the bottom squared. Okay. For the antiderivatives of stuff like this, we actually don't know how to do these just yet. Oh, sorry, we don't know a rule for them yet, I should say. So we will learn the rule for dealing with stuff like this in section 7.1. So for our purposes, if we see a product of two functions, or a quotient, which means two functions divided by each other, right now, so if we see this type of thing before section 7.1, if we see stuff like this, we must simplify these into either sums or differences, functions added together or functions subtracted from one another, sums or differences to evaluate the antiderivative, if I have either a product or a quotient of two functions. Okay, let's do some examples. Alrighty, so example 1, part A, let's find, so the question says find each antiderivative. So there's going to be a few parts to this. So this is part A, and then below this I have part B. Well, let's work on part A. So in part A, I have a sum of a bunch of functions. I have x cubed plus 3 plus something else, and so on and so on. Okay, so our derivative rules say, okay, if I have to take an antiderivative of a sum or a difference of a bunch of functions, you just take the antiderivative of each one individually, and then either add or subtract them together based off of what the signs are that I see. Okay, so let's start this. I know how to do the antiderivative of x cubed. This is a reverse power rule. So the reverse power rule says I add 1 to the power, and I'll get a 4, and then I divide by that power. So I divide by 4. What about the antiderivative of 3, the antiderivative of a constant? So there's two ways to see this. I could do it with a little bit of trial and error. I could do ddx of, well, what do I have to take the derivative of to get 3? And then I might think, oh, I know. I take the derivative of 3x. That's going to give me 3. Another way I can see it is with reverse power rule, because 3 is, it's actually 3x to the 0 technically. So when I do the antiderivative, I add 1 to the power, and I'll get 3x to the 1. And then I divide by that new power. And that's 3x. Okay, so that's 3x there. And you might be thinking, wait, shouldn't I put a plus c for all of these? And if you're thinking that, that's good. I am going to talk about that at the end. Okay, and then for 3 over x, well, 3 over x is just, this is 3 times 1 over x. So the 3 is in front, that's a constant. And the antiderivative of 1 over x is ln absolute value of x. And then to take the antiderivative of 3 over x squared, I can rewrite this as 3x to the negative 2, and now do a reverse power rule. I'll get plus 3x to the add 1 to the power, negative 1, divide by that power, negative 1. Okay, so now this is where I'm going to talk about that plus c. So you might have been wondering, wait, when I was doing each of these antiderivatives, don't I need something like a plus a constant here, plus a constant here, plus a constant here, plus a constant here? And if you did think that, you're not wrong. That's right technically. And if you add these 4 constants together, that's just a constant in and of itself. So because of that, we could just call C1 plus C2 plus C3 plus C4, that whole thing C. So it's just easier to write just 1 plus C at the end, because that's the same as just adding all those constants and renaming it at the end. Alrighty. And let's just simplify this. So this is x to the 4 over 4 plus 3x plus 3 ln absolute value of x, and then I have minus 3 over x plus c, and that is our antiderivative, general antiderivative. All right, let's do part B now. It's another example. So I have the integral of t cube root of t minus 4 root t minus 1 quantity squared divided by t. So one thing I want to point out is the fact that this says dt and not dx just means, so the dt just means that t is the variable as opposed to x as it was in A. To x, I'll say as in A. Alrighty. So for this question, it's definitely a step up in difficulty from the previous example, but I want to give you the opportunity to try this first. So for this question, I'm going to ask you to pause it for about 3 minutes to try this. That may not be enough time to finish the question, but mostly I want you to be thinking about, what are the key steps? How might I begin? Are these things that I know how to take the antiderivative right now, or do I need to do something to them to be able to take the antiderivative? But really seize these 3 minutes and actually try this question. It's really important to test your ability to solve questions like this on your own, because that's what you're going to be doing on the homework, and ultimately that's what I'm going to be assessing on our quizzes and our exams. So it's good to start practicing that now, even in the videos. So 4, 3, 2, 1, pause the video. Pause the video and try this for about 3 minutes. Alrighty, so hopefully you've done that. Hopefully you paused it and tried it for about 3 minutes. If not, I really encourage you to do so now. This is, in my opinion, the most important time in these videos, the time that you take to pause and try problems on your own. Okay, so hopefully you've done that now, and let's start to talk about this. So I have this integral. I don't know how to take the antiderivative of t times the cube root of t just yet, but I can simplify it a little bit so that I can take the antiderivative of it. So I have t, and then cube root of t is the same thing as t to the 1/3. And then this whole thing being squared at the top of this fraction, that's a product of two things. Let's multiply that thing out. So if I were to work out what this whole thing squared is, I would have to multiply 4 root t minus 1 times 4 root t minus 1, and then I'd have to FOIL this out. If I do that, I'll get 16 minus 8 root t plus 1 divided by t dt. One thing that's really important notationally when I do these antiderivative questions is I need to keep writing the integral and the d, whatever the variable is, until we take the antiderivative. Once I take the antiderivative, then I can stop writing those things. But until I actually do, I need to continue to write them. Okay, so t times, whoops, sorry, let's put this in a different color. So I have t times t to the 1/3. Adding the powers, I'll get t to the 4/3. Haven't taken the antiderivative yet. That was just simplification, so I need to put the integral symbol. And with the fraction, what I'm going to do is I'm going to split this up. This is the same thing as 16 over t minus 8. Let's rewrite root t as t to the 1/2 over t, and then plus 1 over t dt. Okay, now let's distribute that negative sign. So I got the integral of t to the 4/3. Let's write that better. T to the 4/3. And then I have minus 16 over t. And then I'll get plus, I'll get 8t to the, if I move this t on the bottom to the numerator, I'll get t to the negative 1/2. And whoops, looking at this now, I'm realizing that I made a mistake. But let me write one more step and then I'll fix it. So I have minus 1 over t, minus 1 over t dt. Okay, so the mistake was when I FOILed this whole thing out. Here I just wrote 16, but this should have been 16t. I forget now if I said 16t and I just didn't write the t. But nonetheless, I need 16t there. So this should have been 16t over t. And then the t's would have canceled and just given me a 16 here. Okay, so now we're at a point where we can start doing the antiderivative. So I'm going to stop writing the integral now. This is reverse power rule. I'll get t to the, add 1 to the power, 7/3. And then I would divide by 7/3. But dividing by 7/3 is the same thing as multiplying by the reciprocal. So multiplying by 3/7. Okay, as we get more and more comfortable with these antiderivative questions, I'm going to start to go through that more quickly. So instead of saying out loud each time, oh yeah, I'm multiplying by the reciprocal, I'm just going to do it. Okay, antiderivative of 16 would be 16t. All right, for this next one, let's see, we have 8 in front. This is reverse power rule. I add 1 to the power. I get t to the 1/2. And then I would divide by 1/2, but that's the same thing as multiplying by the reciprocal, which is 2 over 1. And then for the next term, it's going to be minus ln, absolute value of t. And I can't forget that plus c. An indefinite integral like this means it's a general antiderivative. Okay, I can do it. A little bit of simplification. This is 3/7 t to the 7/3 minus 16t. 8 times 2 is 16. So I get 16, and then I could either keep this as t to the 1/2, or I could write this as square root of t if I want to. And then minus ln absolute value of t plus c. And that is my antiderivative. Alrighty. Let's do one more example. Let's do the integral of e to the t minus e to the 5t plus e. Alright, so this one let's just do together. So I think we can take the antiderivative of these already. We don't need to simplify at all. The antiderivative of e to the t, that one's easy. That's just e to the t. The antiderivative of e to the 5t is going to be minus 1/5 e to the 5t. That was one of our antiderivative rules. But let's just check that so we believe it. To check this, if I were to take the derivative of just e to the 5t, because that's one thing we might have guessed it was, we would do chain rule. The chain rule would give us e to the 5t. That's the derivative of the e part. But then you do the chain rule part, and you multiply by the derivative of the inside. The inside in this case is the exponent. The derivative of the exponent is 5. So we multiply by 5. But that's not quite what we want it to be. We don't want that 5 in front. So to fix that, we could say, okay, what if we did ddt of 1/5 in front? Because putting a constant in front will just sort of stay there. And now when we take the derivative, when this 5 comes down, it's going to cancel that 1/5 and just give me e to the 5t like I want. Okay, awesome. So that is that. Okay, and then this e here, we have to be careful with. E is a constant. And we've seen how to take the antiderivative of a constant. It's just going to be that constant times the variable. In this case, the variable is t. So this will be e times t, not e to the t, like the first term, but e times t. And the derivative of that would just be e which is good. That's what I had before, above it. Okay, I need to put the plus c, and that is my antiderivative. So in terms of our goals for this section, we've now talked about some basic antiderivative rules, and we did a few examples computing antiderivatives. In the next video, we will talk about what differential equations are. Those are equations that have derivatives in them, in which we try to figure out what the original function is. And we'll do some examples.